Hi everyone, hope you're having a good day. So it's kind of loud here today. I apologize for that. So hopefully you're able to hear just me. So we're moving on to our next lecture, which is 2.7, and 2.7 is called Implicit Differentiation. Differentiation. Okay, so our normal derivative that we find is dy over dx, okay? The change in y over the change in x. And that's the most common type. This is called explicit differentiation. So this, wait a minute, I gotta get a better pen. Let's see if the green will work for us here. This is called explicit differentiation. And another way to think about that is it's always the change with respect to x. Okay, so the change with respect to x. Well, give me a minute here. I just want to make sure you can see this green pen. Not great. Okay. Let me switch out then. Okay, so put the green pen aside. Let's go perfect. Okie dokie. Now, this is the type, also the type of differentiation that we use if we have functions. Okay, so used when we have functions. Used for functions. And the nice thing is that up to this point, everything that we've been asked to find the derivative of was a function. But there are other equations out there that are not functions. And so that's when the implicit differentiation comes in. Okay, so we're just gonna do a little bit of practice before we really get into the whole big thing here. So let's say that I was giving you the expression 3x squared. Now notice I didn't put like a function notation on this. I just put an expression up here. And I want you to find the derivative with respect to x. Now that's the way that we're used to finding the derivative. So the derivative with respect to x would just be 6x. Okay, there's nothing tricky about that one. But let's say that I gave you the same expression here, and this time I want you to find the derivative with respect to t. Okay? Now there is no t in that little expression, is there? But I can ask you to find the derivative with respect to any variable I want. Normally we use x and y, obviously, but t pops in a little bit, so we want to get used to that. Now when we find the derivative with respect to t, what we need to assume is that this x here is an equation that has t in it. So the idea behind this is that we're going to use the chain rule here. So we're going to take the derivative of what we see there. So we're going to have 6x, and then we're going to multiply by the derivative of the inside. Now right now, there is no inside. You're like, what do you mean, the inside? But what we're making the assumption is, if it says respect to t, we're making the assumption that there could be a t, that x might equal 2 plus t. We don't know what x equals, right? Okay, it could just be a number, but it could be some other little equation that has t's in it. So this is the way this works. We take the derivative of the outside function, and then we follow it with the derivative of the inside, which would be dx dt. So let's look at this again, but I'm going to use something that we're a little bit more used to here. So let's say that it looked like this. take the derivative of this, we get the 6, and then we leave this guy alone, right? So there's the 6, and we leave that guy alone. But then at the end, we have to take the derivative of what was inside, and the derivative of what was inside is 3x squared in this case. Now, in this case up here, we don't know what the derivative of the inside is because it's not given there. So a lot of times when we see this respect to t, there's there's nothing else there. But we have to keep in mind that there could be. Okay, so this is kind of thinking outside of the box a little bit, right? So, using this implicit differentiation has two main uses. The first one that we're going to focus on in this section is when we take the derivative of an equation that is a relation and not a function. So, as I said, to this point, everything that we have worked with has been a function. But we could see something that looks like this. X squared plus y squared equals 25. All right, now, if that is your equation, that is not a function. And hopefully you guys recognize that guy. That guy is a circle, right? So we have a circle with a radius of 5. Okay, so a circle is not a function, but a circle could definitely pop up. We might be interested in a circle in calculus. Well, if we're doing a circle in calculus, we can't use explicit differentiation. We use implicit differentiation. So we're going to use implicit differentiation when we have a relation. Okay. So here's how this works then. There's no t in this one. That was just for that example, just to kind of show you that you could throw anything in there, okay? So just don't have to worry about any t or anything. It's just x and y's. But as we go through this, remember that we're finding dy dx, or y prime. So as you look at a relation, every time that you see a term that has only an x in it, you're good to go. You take the derivative like normal. But every time that you see a term that has a y in it is where this implicit differentiation comes in. So you're going to take the derivative of the y term, but then you're going to follow it by the derivative of the inside. And again, we don't know what the inside is, but there is the assumption that y equals something. Y equals x plus 7. Y equals x squared over 2. Okay, we don't know what it equals, but there's the assumption that there's the chain rule going on here. Okay, so there's a little chain rule going on. Okay, so this is how this works. So we're just going to go right underneath it. We're going to say 2x. That one's the easy one. It's only got x's in it. Then here we're going to go plus 2y, but then we're going to immediately follow it by a y prime. Okay, so anytime you take the derivative of a term with y in it, times y prime. And then the nice thing is on this side, we just get 0. So a lot of the times when we're dealing with these guys, there's just a constant on one side, which makes life easy. Okay, so that is the implicit differentiation, but there's a problem because we want this to be y prime equals, so we gotta move some things around. So a little bit of algebra here. So we're gonna subtract the 2x, so we'll have 2y y prime equals negative 2x. And when we divide by the 2y, we end up with y prime equals, and now it looks like just negative x over y. So a little bit more work to get to your derivative, but we're still able to do that. But now I can ask you questions about that. I could say, excuse me, what am I going to say? Find the tangent line to x squared plus y squared equals 25 at the point 3, negative 4. Okay? So just like we've seen in other sections, I can ask you to find tangent lines here as well. So we have our derivative, and that derivative is going to give us the slope, right? But this time, normally we would just plug in an x value into our derivative. But this time, in order to get our slope, we need to plug both the x and the y value, don't we? So we could say that our y prime, or our slope, is going to be negative 3 over negative 4, or just 3/4. Okay, so we need both of these guys up here. So that's our m. And then let's see, we'll go y minus, so that'll be plus y plus 4 equals 3/4 x minus 3. And we'll distribute in. So 3/4 x minus 9/4. And when we subtract the 4 on this side, we'll subtract it as 16 over 4 over here. So we end up with y equals 3/4 x minus 25 fourths. Okie dokie. All right, so we used implicit differentiation, and we were able to come up with the equation of a tangent line to that relation over there, to that circle, because remember, it is not a function, it's a circle. Now, circles are the nicest guys that we deal with when we deal with relations, but they don't have to be that nice. So let's kind of step it up. Let's look at some different examples here. So let's say, oh, they don't start too bad here. So let's say we have y cubed plus y squared minus x squared equals negative 4. Okay, so this area of math is not my area of expertise. So these would be considered polar coordinates, and these are different types of graphs that are similar to circles. So an equation that looks like this, not a function, but an equation that looks like this could very well be like an equation that makes a flower. Okay, so you have a bunch of petals on a flower, or it makes kind of like a curly Q or something. But whatever it is, it's not a function. And these equations, they're super helpful, especially for people in the computer business that are doing like animation and trying to make computer programs and that kind of thing. So they definitely are out there, They don't really apply to our class, but we're gonna use them a little bit to get to where we're going, okay? So let's find the derivative of this guy. Now remember, the way this works is every time you see a y, take that derivative and follow it with a y prime. Every time you see an x, you don't have to worry about anything, okay? So here, we're gonna go 3y squared times y prime plus 2y times y prime. Then we're gonna do minus 2x, but we don't have to put anything on that because that's a regular x. It's the way that we're used to taking the derivative. And then again, luckily the other side is just 0. Okay, so piece at a time, y's get the y prime attached to them, x's, don't worry about it. Now, we want to get this y prime alone on this side. So the worst part of this is actually the algebra at the end. So let's move the negative 2x to the other side. So we have 3y squared y prime plus 2y y prime equals a positive 2x. Now, in both of these terms over here, we have that y prime. So we can factor the y prime out to the front and leave 3y squared plus 2y equals 2x. And then we can divide out. So almost always when you're doing these guys, after you simplify, I don't know why I put the parentheses there, I don't need that. After you simplify your derivative, you're going to end up with a fraction. Okay, so the fraction definitely comes into play. So that's another reason why people are like, oh, I don't like these kind, because there's always a fraction in them. Alrighty, so let's do another one. Let's step it up a little bit and see one that's got a little bit more to it. Okay, so this time we're going to do xy plus xy squared equals 7. Now, this one maybe doesn't look even as ugly as the one before, but when I look at this, I see something way uglier than the one before, because here I see a term that has both x's and y's in it. Here, each term just had one variable in it. Here we've got to mix and match. So you know what this needs, unfortunately, is the product rule. So we have to use the product rule in order to find the derivative here. Okay, so remember, product rule, take the derivative of the first guy, so that'll be 1, and leave the second guy, so that'll just be 1y. Now we haven't taken the derivative of the y, so we don't have to do any y prime or anything. Plus, leave the first guy, x, take the derivative of the second guy. Well, the derivative of y is y prime. So that's just that first part there. Okay, that's the derivative of just that first part. Now we've got to do the product rule again over here. So we're going to take the derivative of the first one, the x, 1, leave the y squared, plus leave the x, take the derivative of the y term, so 2y, but that 2y needs to be immediately followed by y prime, right? Because we took the derivative. And then this is going to equal 0. So when you have to use that product rule, it's definitely going to make this bigger and uglier. Okay, and it's very, very easy to forget to use the product rule on this guy. And then the easiest thing to forget is this one. You get the product rule and you're all proud of yourself, and you get to the end here and you go, oh, the derivative of y squared is 2y, and you forget to follow it by the y prime. Okay, so can't forget that y prime. Okay, now, like we did in the other example, we're going to move everything over that doesn't have the y prime in it. So we'll have the xy prime plus 2xy y prime equals, and we'll have negative y squared minus y, right? If we move both of those guys over. Now again, we can factor out that y prime here, so we have x plus 2xy equals negative y squared minus y. And last but not least, we will divide. So negative y squared minus y over x plus 2xy. Good there? Okay, so let me look out for one kind of uglier one. And whoa, that is a doozy. All right, well, I found an uglier one. Okay, so that's actually very ugly, but whatever. Okay, so let's go y squared times x squared plus y squared equals 2x squared, and they're going to ask us to find the slope of the tangent line at, what point did they give us? Oh, at least the point is nice, 1, 1. Okay, so at least that, making life easy there. Okay, but definitely the ugliest one we've seen so far. We've got multiplication on this side, and then the other thing is we don't have a constant over here, so there's no 0 sitting over here for us when we take the derivative. Okay, but we can still deal with this. Now, just like before, it would be a good idea to distribute it. Okay, so just like when we're doing a regular derivative, if you can keep from doing product rules or chain rules or quotient rules or whatever, go for it. So before we start this guy, let's distribute in here. So we're going to have x squared y squared plus y to the fourth equals 2x squared. Okay, so we still have the product rule going on here, but at least that's simpler, isn't it? Okay, so it changed it a little bit, made it a little bit easier here. So we definitely have to remember that product rule there. Don't forget the product rule. So take the derivative of the first guy, 2x, leave the second guy alone, y squared, plus leave the first guy, x squared, take the derivative of the second guy, 2y, which immediately gets followed by a y prime. Okay, so there is our product rule for that guy. Then right here, luckily no product rule, we just have to take the derivative of y to the fourth, which will be 4y cubed. But what did we just do? We took the derivative, so we follow it with a y prime. Then on the far side, we're just taking the derivative there, which would just give us 4x. And it's an x, so we don't have to worry about it. Okay, look all right to everybody? So piece at a time, don't do the whole thing all at once. You start with that, then you move to that, okay, piece at a time. Okay, now again, y prime's alone on this side. Let's get that guy over to the other side. And I'm also gonna factor out that y prime at the same time. So we'll have 2x squared y plus 4y cubed equals 4x minus this guy, right? Minus 2xy squared. Okay. And then the last thing we have to do is just divide that guy to the other side. So y prime equals 4x minus 2xy squared all over 2x squared y plus 4y to the third. Okay. Now, proud of ourselves, we got this one. It's the ugliest one we've seen so far, but don't forget that they wanted the slope of the tangent line. So they want us to plug in ones all over there. And what's the nice thing about plugging 1 in for every single one of those guys? It's not going to change anything, is it? So it's actually just going to give us y prime equals 4 minus 2 over 2 plus 4, which will give us 2/6 or 1/3. All right. Look good? One more problem here for you. And this one is gonna, I'm getting you into what we're gonna do in our next section. So this problem is a little bit different. We're getting rid of the x's and y's and changing things up a little bit. So let me move over here. Okay, so the demand function for a product is P equals 2 over 0.001 x squared plus x plus 1. And we want to find the rate of change with respect to P. Okay, so the demand function for a product is given there, and we want to find the rate of change with respect to P. So not with respect to X, but with respect to P, which means what we're looking at here is dx dp. That's what we're interested in. And here's the thing. That means anytime that we take the derivative of something that has a p in it, we're good to go. But anytime we take the derivative with something that has an x in it, we're going to immediately follow it by dx dp. Okay? Same idea that went over here. We're immediately following it by its derivative. Now the worst part about this is that we're going to have to do this dx dp a number of times, right? Because we have x's in the problem. But the worst part of it is that this is also a fraction. And so in order to do this, we're going to have to use implicit differentiation, but in the form that it's in right now, we're also going to have to either use the chain rule or the quotient rule. And with implicit differentiation, that does not really sound like a great plan to me. So what we're going to do is we're going to fiddle with this guy a little bit. So you don't always have to just jump right into the problem and do it. When you have something ugly like this, we can take this apart a little bit. So first thing I'm going to do is, could we do this? Could we say p times 0.001 x squared plus x plus 1 equals 2? Okay. So can I multiply both sides by the denominator and end up with this? And we certainly can, can't we? And since we're doing implicit differentiation, it doesn't matter how ugly this is going to look. Now, we could work on it at this point looking like this, but another thing we could do is we could actually divide the p out to the other side. Okay? And then we end up with 0.001 x squared plus x plus 1 equals, and now over on this side we have 2 over p, but if I wanted I could write that as 2p to the negative 1, right? 2 over p. So now what I've done is I've just rewritten the problem. We haven't done any derivatives, we haven't changed anything, we've just rewritten it. But by rewriting it, look through here. Do you see any product rule? Do you see any quotient rule? Okay, so this started off as a quotient rule. Here it was p times that mess. Ugh. Now this is strictly one at a time. Boop, 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 boop. Okay. So messing around with it a little bit can ease the pressure of taking the derivative. So that's why the implicit differentiation can be helpful to us. If our function is really ugly, move it around a little bit and do implicit differentiation. Okay, now remember though, every time we take the derivative of a guy that has an x in him, we have to follow it with dx dp. So that means we're going to have 0.002x dx dp plus the derivative of x is just 1. But because it was a derivative of x, we follow it immediately with dx dp. Derivative of 1 is just 0, so it goes away. So we're on the far side, we bring down the negative. So we have negative 2p to the negative 2, right? All right, now remember, the idea is we want this guy alone. Yes, this guy alone. So we're going to factor out dx dp. That'll leave us 0.002x plus 1. And then finally we end up with the derivative of x with respect to p, which is new to us, equals negative 2p to the negative 2 over 0.002x plus 1. Okay. Now, in this form, with this dx dp thing that we were trying to find and everything, this would have been a real pain in the butt. But by this manipulation a little bit and using what we did in the last couple examples, it really wasn't that hard to get to this, was it? Okay, it really wasn't that bad. Okay, sound good to everybody? Oh, and wait a minute, I guess if you don't like this notation, we can bring that negative square to the bottom. So this would be negative 2. And then on the bottom, we would have p squared, and that guy and then we would still have this 0.002x plus 1, okay? So if you're like, I don't like the negative exponent, that's what it would look like without the negative exponent. Okay, still something a lot easier than what we would have been able to do over here. Okay, sound good to everybody? Okay, so the idea is to practice with 2.7, get into the implicit differentiation because 2.8 can be a doozy, okay? Really, 2.8 is the big one. Okay, everybody, have a good day.